Yeah. Okay, so hello to the people online and to the people in the room. Thanks for coming. I'm very happy to welcome Professor Michael Herzog, who's visiting from the Brain Mind Institute at the EPFL in Lausanne. And Michael is Professor of Neuroscience there. And Michael has some diverse research interests in a number of different areas. He's doing vision science talk today. He's also does research with EEG, a lot on individual differences, and also research on schizophrenia. But yeah, Michael has some controversial ideas. I hope he's going to stir us up a little bit, and looking forward to hearing your talk on vision science. Thanks, Michael.
Thank you, everyone. Thanks for the kind introduction, Jenny. It's a real pleasure here. And actually, I'm still a little bit dizzy from the cool demonstration I just saw. This is a little bit more a conceptual talk today. And just to preface it, at the end, I will claim that objects don't exist. So then you're prepared for it. You have a little bit of time. Let me. What can I follow to work before?
Is it that one? Oh, maybe we need to click on it.
I'm going to do it here.
I think we might just need to click on the screen or something.
Oh, what's the audio issue?
We were just having trouble moving the slides. The audio issue's gone now. But,
Oh, okay.
Okay.
So this works. Okay.
Is it working?
Yeah, no, it should work. I don't know.
Okay, good.
Let's click some stuff.
Okay, so here we are.
Thank you.
So first of all, I have a little bit of a starting point about what perception actually is historically and philosophically, and I will talk a little bit about Gestalt. Intuitively, there's not too much to explain about perception. You know, there's a candle in the outer world, and that's why we see a candle. And usually, if you see a candle, then there's a candle in the external world. Okay, we're not talking about dreams and hallucinations. But the idea is that there is a one-to-one mapping, that's mathematically a bijection between what's out there and what we see. And that's what we assume usually in perception research. And also in science, we believe that we can trust our senses. And for this reason, we know what the world is, and then we can, whatever, investigate the stuff we want. That's the idea. So that's basically in accordance with our intuition and also quite of particular British philosophy. And it's something I'm going to destroy. The idea is that this actually is quite direct in some ways. So the idea is that we more or less directly acquainted with the objects. But we know that this is not true because, because of the laws of optics, actually an object projects upside down and left, right, inverted on the retina. So we are not that close to this. So there must be a transformation, at least from the retinal image to the representation we have. And whenever there are transformation, or whenever there is something in the brain, then things can go wrong. And they go wrong. And I think for color vision scientists, I don't need to show you this, but I think you all know this, isn't it? But for those who don't know, there are 4 colors and one color is missing, and I think you know which one it is. I think you see blue, green, pink, and orange. Yeah?
Yeah.
But this is 4 colors, but in fact, there are only 3. So one is missing. Which one? Orange.
Yeah, I'd say that as well.
Yeah.
I don't know.
It's blue.
Ah.
And I can show this to you. We just remove pink and orange, and you can see this is green. We can see here how the green basically changes to blue. This is a version of the white effect. And even if you know that blue doesn't exist, it is still something you perceive. You cannot undo it, and even knowing it's not there doesn't help you too much. So this is a problem about this bijection idea, because there are things in the brain we see which are not out there. And for this reason, actually, the philosophers like Kant and Fichte, they said, no, but we cannot really know about the world. We have no direct access to the world. The world is not there. It's not given. It needs to come through the senses. And obviously, the senses are not that good as we believe they are. And for this reason, I said, oh, let's stop it. Let's talk about the things we know. That's basically our thoughts and our percepts that we can do research on. Because to the external world, we have no direct access. And this was actually taken up by the Gestaltists, even they were not Kantians. Actually, this is historically a little bit complex, but they still believe to explain perception just by the percepts themselves. Basically, what they wanted is they wanted to explain perception of a whole by the perception of the parts. That was their idea. And of course, we can do something like this. So this means, can we predict the perception of the whole by the appearance of its parts? And I think we can do this. So, but your task is right now to move this outline of a rectangle down, so it basically just surrounds the circle. Can you do this in mind? Yeah, I think you have an idea how it looks like. Looks potentially something like this. Right? So we can do this. Seems to be not so super complicated. Here's another one. It's actually the same idea. You get some battlements here. Here the straight lines and this curvatures. And the task is again to move it down so that this basically, this end touches this end. Yeah. Can you do it? No, you cannot. At least I believe you cannot. Have you ever, yeah. Even if you can look it up right now and can try it again, you cannot basically, you know how it looks like, but you cannot do this yourself. And the interesting thing is that the ownerships here have quite changed. For example, here, you're binding the straight line with this curved segment. What you're doing here is you're basically binding all the curved elements together, and that gives you a sine wave grading, and on top of this square wave grading. So the ownership of the elements has changed in some way. In this way, that's what the Gestaltist said. We cannot basically predict the appearance of the whole by the appearance of the parts. All the information is here, is on the screen, but you're still not able to basically put these things together. That's basically the Gestalt idea. And they came up with a program that tried to explain these things. Yeah, that's what I said before. They tried to explain these things. But what is important for us is we know that there is more in the brain, or there's more in your percepts than there's in the external world. I think that's the important thing for our talks. So that means in some way we cannot talk about the fundamentals of vision in general, because this bijection doesn't hold. So we need to ask two questions. What is fundamental out there? What is really in the world? What we usually believe we get through vision or other types of perception? And we need to ask what are actually the perceptual processes. And once more, these are not one-to-one. So we have two questions. That's what I want. It's the message of the first part. And we just talked about, sorry, let me go back one slide. We thought, oh, there's more in our perceptual world than it's out there. The opposite is true. True. And I think you all have seen this before. You see two faces of Margaret Thatcher, and they all both look quite nice to you, isn't it? You know, they are not the same, but if I'm turning it by 90 degrees, you see this oddity right away. And if I'm turning it back, you know they are not the same. And you might even see that the eyes are actually rotated in the mouth too. Still, you don't see the oddity in Margaret Thatcher's face. That means we don't have representations for the whole configuration if faces are inverted, but we have representations for the spatial configurations if the faces are upright. That means there are many things in the external world we can't see. That means this one-to-one mapping is an illusion in some way. That's what we believe about perception, but it's not true. So much for the introduction. My point is that this Gestalt approach disappeared with World War II for various reasons. My reason is to explain perception without a latent variable, without a cause, just doesn't work. Because many things in the percept depend on what's out there. And we will come to this later. I believe there is something in the external world, but it's not candles. That's the idea. There's not ordinary objects. That will be the link at the end. Okay, good. Let's come to our 2 days research, and I think the story has totally changed. We are back to the classic approach. We believe there are ordinary objects in the external world, like candles. And what we do, what most people do on planet if they do vision research, I think the same is true here in Sussex, is we basically pursue a causal approach. So we assume, yeah, there are some stimuli or some external objects, and then we see what happens actually in the brain. So we know, I think you all know how this works. We look at the retina, the LGN, and so on and so forth. And we see what happens in these areas if a stimulus is presented or changed. In this case, what people discovered is there is a problem with this projection too, because the world is three-dimensional, but the projection on the retina is two-dimensional. So in some way, we need to reconstruct the image, or we reconstruct what's presented on the retinal image to a 3D world representation. And this is mathematically impossible to some extent because you can never go from 2D to 3D. That's a little bit the idea. So actually that errors occur is quite normal because this is in some way a reconstruction process that's mathematically under constraint. It's an Ilpos problem. That's the idea. So that's why they say, yeah, that these errors we just have seen, they're just totally normal. They actually prove that this approach is true. So once more, the idea in our view, at least or most people do it in these days, is yes, there are objects in the external world, and yes, there are representations, but there is this intermediate representation on the retina, for which reasons we need to clean it up. So vision is basically a big laundry in some way to get the poor retinal representation into a good reconstruction of the image. That's the idea. So that's what I said before with the errors. And then we're ending up with a scheme like this. I think that's textbook knowledge. That's what's in the external world, for example, these squares, and then we have neurons in V1 that are sensitive to edges. And what we do is we pool the information. For example, here we have edges and neurons that are sensitive to vertical and here to horizontal lines, and then we combine them. And if you're combining these two neurons, you get, for example, a neuron that's sensitive to an angle. And if you have 4 of these neurons and we combine them, then you can create a detector for a square. That's a little bit the idea. The important thing is that you pool information. That means you go from low-level neurons to small receptive fields. You pool them together, you pool the outputs of these neurons to get neurons with larger receptive fields and so on and so forth, and to more complex features like objects and shapes. That's a little bit the idea. And I think that's a good idea from an engineering point of view, because you're breaking down a complex problem into solvable, independent, smaller problems. I think that's the take on, that's basically the idea. This type of architecture is quite successful. That's something we have in the deep networks, and we know the deep networks are really super good in object recognition. They don't do anything else. They just, it depends on the architecture. You can get extremely super good results by just following this procedure and just using backpropagation. So that's a good idea. So let's compare these two ones, the Gestalt and the physiological approach. In the Gestalt approach, we believe that the wholes determine the perception of the part as much as the other way around. That's what we have seen. We have these irreducible things. You can put two parts together and you get something totally different. You cannot predict how the whole looks like just by looking at the low-level structure. That's the idea. That's just the opposite in the physiological approach, where everything high level is determined by low-level processing, but not the other way around. And in the Gestalt approach, the gestalts of the objects are primary and they're not reducible, and it's just the opposite in the physiological approach. Okay, good. You can explain quite some stuff with these things, with these approaches, and one is the crowding one, and you can experience this yourself. You're staring here at the bull's eye, and you're watching out for kids. Okay, don't move your eyes. And I think it's easy to see this kid, right? But it's much harder, don't move your eyes, to see this kid, right? And the point is, this is not crowded, and this one is crowded. And you get the crowding in particular because the color of the t-shirt is the same as the color of these construction signs. So if you send your kids to school, this is practical advice how to trust them in something. And then, of course, it's more important actually to get this kid than this kid, because this is heading away from your car, because this is basically running into your car. So it's really crowding, and what I want to say is really important in some way. Good. And this crowding can easily be explained in this framework. The idea is basically you have these low-level features, and under good conditions, you get object recognition that basically when the pooling mechanism operates well. And in this case, crowding is basically unsuccessful object recognition. You're binding or pooling things together that should not be pulled together. That's the idea. And one of the consequences is that actually the more elements you have, the stronger should be crowding. Yeah? You're pulling more information. You cannot get better. And that's what I'm going to show you is not true. Yeah. Okay, so we did a rectangle discrimination task, first time on planet. It's totally stupid task. You say if the x-axis is longer than the y-axis, which is here, so you say wider. In this case, this is shorter and this is longer. You say narrow. You push a button. And then we do a task and we plot it as thresholds. That means high thresholds means bad performance and low thresholds means good performance. You can see that the participants are somewhere at 300 arcsecond, whatever this means. And this is actually presented in the periphery. So at 9 degrees, you watch focusing here and you basically looking at the periphery. Yeah. Okay, good. There's nothing special here. Then we add 3 squares to the left and to the right. And what we get is a crowding effect. Yeah, that's just the same as with a car. You have the kit and then you have the construction signs. Here you have the target. You get this is the construction signs and you get worse. Nothing special, plus a crowding effect. We have another task. Here you need to say the lower line is to the left. You push left button. Here you push right button. And our threshold here is around 100 arcsecond. What we do next is we have a square. We just surround it by the square. And you can see again, crowding is really ubiquitous. It's always there and it always exerts super huge effects. So you see we go from 100 to 700 arcseconds. So that's a factor of 7. Huge effect in some way. Good. Nothing special, it's just another crowding effect. And then we combine the two, and you can guess what's going on to happen. So the task is again to do this Vernier task, and what we have seen is the square makes the Vernier much harder. What we have seen is that these squares actually make the perception of this square much harder. So you would expect that we get something like super crowding performance, can only deteriorate what we have said, yeah. If I hit you 1 time, it hurts. If I hit you twice, it hurts more. That's the idea. So we should get something like super crowding. We have a lot of negative interference here. And what you can guess is it's not going on to happen, just the opposite happens. So the Vernier alone is quite good. We get this normal crowding effect, but adding more elements does not lead to higher crowding as expected. It leads almost to the level as if there were no flanking elements at all. So you're basically almost back to the level of the target alone condition. So crowding of crowding leads to uncrowding in some way. And that's a little bit surprising. It's extremely hard to explain with all these frameworks where you pool information or where you have lateral inhibition or something like this, because all these elements don't carry any signal. They can only make things worse. And that's not the case. Yeah, so that's what I said before. And so what we believe is actually that all the information that comes into the eye is kept for a while, and then you compute first the Gestalt, you compute structures and objects, and then actually at the end, you determine what the percept is. So if you have this Vernier, this square, you pull everything together. That's clear. But if you have these many squares, I think you see it yourself, what you're seeing here is an array of squares. And then there's something that doesn't fit in, which is this Vernier. And for this reason, you get actually 2 types of objects. One is a texture of squares and a single element. And for this reason, the decoding goes away because you have access to it. Once more, the square is always here. But the square itself basically loses its identity because it becomes part of a background. And I think that's something what we believe is going on for a while. I will show later on that this is not only true for space, but also for time. I think information comes in, we wait for a while, we compute the best interpretation, and then only if things belong to each other, then you get crowding. If they don't belong to each other, you never get crowding. That's it. And I think that's not totally surprising. It's not a lab type of stuff. It's something we need to solve all the times. We know that we're looking for edges to reconstruct the object, but the edges need to belong to each other. You don't want to mingle with edges that come from totally different things. So in this case, what you for example, this is good edge in some way, or this is good edge here, because it belongs to the house. This is bad edge, because it doesn't belong to the same object. So you need to segment the way in different layers first, before you start computing this. And that's what we believe is you do first, and then you do feature detection. That's the idea. So that means we are back to the Gestalt times. Gestalt is first, and the higher level object representations determine how you go to see things. That's the idea. So it's just the opposite to what we believe. Yeah?
Don't you need to do feature extraction to do the segmentation?
Yeah. You need both. You need to both.
That's what you said, it's segmentation first and then feature detection.
Okay, temporarily, I don't, that was a too strong claim. I just want to say, sure, you need to do you need to do feature extraction to get segmentation. I think it's a closed loop thing. We will see this just in a few minutes. That, yeah, you're totally right. You're totally right. This is a closed loop process in which you try to come up with the best interpretation by recurrent processing. That's a little bit the idea. But you cannot determine, the main message is you cannot determine what's going on here just by looking at the spot itself. That's basically next slide. Yeah. So what we have here is, so this was about qualitative aspects. I think the quantitative aspects are as interesting as just what we said. So if you look at this, so here we are quite good with the learning. Then we get this huge crowding effect here. Then we add a square here to each side and get a bit better. 2, 2, get a bit better. 3, 3, you're even better. That means what matters is the entire information of the entire array. It's not just one square is going to do it. You get incremental effects all over the time. Our interpretation is because it becomes more and more clear that this is a texture. What's interesting is that this is actually 20 degrees. And that's almost where we have good vision. Sure, the visual field is 160 or something like this, but from 40 on, you have no object recognition at all. So 20 is more or less the good part of where we have good vision. That means here we have 100 arc seconds, and if we have 20 degrees, that's 72,000 times larger. That basically just means if you want to know what's going on here, at this point, you need to know what's going on more or less in the entire room. That means, once more, this localized approach cannot work. Everything basically depends on everything. That's the idea. So you need to solve these two problems simultaneously. That's the idea. Okay, so much about the human psychophysics. You might actually ask, yeah, but what about the networks? The networks are super good vision systems. Do they reproduce these results? And yeah.
I mean, in your previous experiment, now when you've got 3 squares either side, if you were to suddenly switch one of those flanking squares by another shape,
it breaks down right away.
So it comes back again, the crowding.
Oh yeah, if you just move the square up here a bit, you're dead. Not you dead, the crowding is back. We have hundreds of these experiments. You can go into the next direction. You can have, for example, what we have is, we have a square here, a star here, and a star here. You get super strong crowding. Then you basically copy the whole thing, then you get 3. Then you get the uncrowding. Then you move them by one element spacing, and the crowding comes back. You can play hundreds of games here. Good for students because you can publish a lot of things. So we asked the question, what about the deep networks? And what just comes out is that the deep networks totally fail on these type of tasks. So we cannot see this, we got 1,038 deep networks, and classic one is AlexNet, and you can see his percent corrector. You can see, yeah, it's trained on Vernier, it does good with Vernier, and it shows also the crowding effect. But if you add more and more squares, you don't get any improvement at all. If there is something that actually you get the super crowding you would expect in some way. And that's true for almost all of the other networks too, even recurrent ones and so on. So as I said, we tested 1,038 and they all failed. There was one exception, and that's ChatGPT.
Wow.
And that showed perfectly these type of effects.
How do you get ChatGPT to do visual crowding?
we just treat it as a normal subject. We present the image
Okay.
to the network, and then we ask, could you please tell us what the offset direction of the Vernier is? And then
prompts.
Huh?
Through the ChatGPT, through the prompt you ask this.
It's a professional ChatGPT thing. So you present these things, yeah, and then you ask questions as you use ChatGPT.
Wow.
But then it probably knows what the crowding effect is and bases the answer on.
We don't know why. It could be that maybe, contrary to you, ChatGPT has read our papers. So I gave this talk recently somewhere else, New York, and I said it's only ChatGPT, and the student managed during the talk to actually do this with another system. I think it's called Gemini or something like that. Gemini, which is, I think, Google's, and this was good too.
Interesting.
Yeah. As I said, there is this option that the system that this doesn't come by visual information. It might actually come by language information, but we don't know. We have no idea. But all other networks, in particular those we programmed ourselves, where we don't have access to all of them, but many we programmed ourselves. The message is clear. They all fail on this.
So it's all CNNs, or
Yeah.
do you do shifting?
And all types, we have recurrent ones, we have the transformers, everything that's on the market.
Yeah.
And really super big ones. Yeah. And I have to say, this is not the only psychophysical task. We have even contour integration and so on and so forth. The networks don't follow the human visual system. And I think, if I may, what turns out is that all of these networks don't have segmentation. And the only network that also does a good job, which we didn't test here, are the capsule networks. And capsules have an explicit segmentation stage, and they do quite well. And there's another model by the Cross-Bergen type of model. It's called the Lamina. That does a super good job. But that explicitly made to compute segmentation and grouping operations. These networks can do this. All other networks cannot. Okay, then you might say, oh, this is true for these Verniers and with these people in Switzerland. Maybe this is just something very, very specific, but it's not. First of all, it's not new. People found similar things early on. It works for Gabors, actually it works in haptics, so we blindfold people with what they did, and then they touch the stimuli. It works in audition, it works for textures and something like this. Everything we tested shows these type of effects. The only thing where it doesn't work is actually for contrast and luminance. That's where low-level properties play a role. In color, you get the very same effects with color too. Okay, good. So this is a problem with this physiological approach, because the physiological approach tries explicitly to explain the complex problems of vision by modularizing the information, by basically explaining everything from low level to high level. That's not true. So what we thought is, okay, maybe the Gestalt laws can do this. This is actually this place we just talked about before. Discussed before, and we had a lot of this symmetry, all of these Gestalt cues, and try to see if they work. Like here we have symmetry cues. Maybe I can show you the symmetry cues. Yeah, you see this here. This is our symmetry axis. But no, it's about the Vernier here, and we always in the middle have the Vernier with the square. And then we have these stars. And we have good continuation here, we have closure here, repetition here. This is our controls. And just turns out, no, Gestalt laws cannot do this too. And the reason is rather simple. Here the hatched line gives you the performance just for the Vernier within the square. So this is our reference, there's strong crowding. And then you can see, yeah, for some of these symmetry cues, you get actually worse. So you get super crowding here. But there are others like this one, where you get much better, and others very super good. And that's true for all of the Gestalt cues. So the Gestalt laws cannot explain these results too. So in some way, we're back to square one, and I have to say, I'm sorry, I just wasted half hour of your life. But the big question is what's going on here. And I think it's going to hint what you said before. The point is, what we need is dynamics in this. You cannot this is a typical chicken egg problem, In some way, you need the lower level information. On the other hand, you have the high level information. In the next part, I'm just showing this is in fact true. And actually, it goes on for almost half second. That's the idea. So what we did is just, again, an experiment like this. You have percent correct here, again you have a Vernier task, and actually here the lines are smaller, here they have the same length, and here they're much larger. Now what you can see is this is actually worst, this is medium, and that's best. And you can see these effects yourself, you know, this is much easier than this. Again, it works on this stupid PowerPoint presentation in some way. But it's exactly the same, I just made the lines longer, yeah. And this should be worse because there's the most energy here in it. This should be medium and this should be actually best, but that's not what we're going to find. And the explanation is again the same. If I ask you how many objects do you perceive here, you would potentially say there's a grading, right? One. Or maybe you would count the lines, which you actually cannot do that easily. Here you would say 3, you know, a grading with long lines here, here, and something in the middle, the same here. But that's the idea again. You worst here because you group everything together, and by this, the single elements lose their identity. It's like if you see the tree, the forest, then you don't see the trees. That's a little bit the idea. Okay, so then we did EEG. So we have high density EEG, and we compute global field power, which is the variance over the electrodes. So it's reference free. Doesn't really matter. What matters is that higher amplitudes mean there's more processing, whatever that means in the brain. What you can see is here at 0, we present these 3 squares, you know, one after the other. And then in 100, you find this P1. This P1, and let's go P1 component, thank you. Sorry. Maybe still it's flickering stuff. The P1 components, what you can see is what you expect from this. You know, you get the highest peak for the grading with the longest line is just because the P1 reflects the low level properties of the stimulus. It means luminance in this case. So this is highest, this is medium. Not surprising. And then you can see that the green line and the blue line swap, and this now basically resembles the performance. Yeah. So these things, and they correlate moderately with each other. You can see this is highest, this is highest, this is lowest, and this is something. The important part here for me is that a more retinotopic and low level of representation has changed into a representation of how you perceptually organize the stimulus. And we have done a couple of control conditions to really show it has nothing to do with performance. It's really about how you perceive these stimuli. I don't want to show them to you, it's a little complicated. But this reflects right now how you perceive and how you have organized the stimulus. That's what I've said. But that depends on your brain wiring. That depends that you make this transformation. We talked about that, these transformations in the brain. That means someone else could have done it differently or could do it differently. So this is not about the stimulus. The stimulus are just the lines. The organization integrating, that's something you have done. That's not in the world. There are no gradings, there are just lines. So this transformation is something specific to the wiring in your brain. That's the idea. And that's what we actually believe. That's actually the point, what I said before. Here we have just squares, and basically you want to group them into one array, and that you want to basically move to the background. That is basically going to happen at this N1 component. That's the idea. And then if you have done this, then you get this element back, and that's why you're so good with it. That's the idea. As I said, the important thing is that we have these transformations, and they depend on your brain wiring. That's going to become important at the end for the object. Okay? So in some way, we talked about that actually the way we see perception is not, usually we believe it's super direct, basically there is something, then we see it. So we are really far from it. Actually, it's not only upside down and something like this. We're presenting something and then a lot of things going on in the brain, and at one moment we perceive it. So it's not only a lot of transformations in the brain, it takes also quite a while until we see this stimulus. And what I want to show you in the next part is I want to show you that this actually takes on up to 400 milliseconds, something like this. And the proposal is information comes into the brain, all is there in your little basket. It's not conscious for you. You put it all in, and then you basically see what is my best interpretation. And then you have a conscious person. That means we are not conscious most of the time, just at certain moments of times for a very short time. What exactly happened, we have no idea. But at least I don't know so much about what happens with the consciousness, but I'm rather confident that we have these long periods of unconscious processing. And that's what I want to show you next. So actually what we do is we basically start from this demonstration here, from this stimulus, and we just present the lines one after the other. So we start with the central line and then these ones and these ones. And that looks something like this. And I think it's going to work. Did you see it? Yeah, you saw a stream of line? Okay. So did you see that at the white dot there was a line in the middle? Okay, there's a question here. I'm going to present you two sequences. The first one has a line at the center, and the second one does not. From the second frame on, everything is the same. Okay, and your task is to say, is it this sequence with the first line, or is it this sequence without the first line? And I show you two demonstrations, and you need to tell me which one it is. Okay, let's do it. Okay. Who saw it in the first? Who believe? Once more, one has the line, one does not. Who believes that this line was in this presentation? 2, 3, 4, in this? Okay, half. It's good. Basically shows you have no clue. But I think you all had hard times to see it. But it is in one of the frames. I can show this to you. It's just going to occlude this. Just put this on top. It was here. It's not here. So with this, so if the line is presented itself, you can clearly see it. It is this meta contrast procedure that basically removes the line from your consciousness rather effectively. And that works for almost for everyone. So that's what we have established. So you don't see the line. The surprising thing is, if you give this line an offset, either to the left or right, once more, this element is not offset. And all these lines are not offset too. Still, you see this offset in the stream of lines. So this is in some way taken off and attached, glued to these straight lines. It's not a super large effect, I need to admit, but it works quite reliable, at least for majority of subjects. So in some way, we can basically remove something from consciousness and basically it reappears at one moment of time at other elements. That's the idea. We can give this quantitative expression. So here we have our stream. We ask subject to pay attention to the left. And then we ask them just to push a button. We just say, look at the left stream and tell us which offset you see. And usually it depends a little bit on the subject. Often they see actually the last line offset or all lines offset. And depending on the offset size, they reach 80%. Yeah?
Do you ask for their confidence levels? Like
No,
but
that's something people are doing right now. Yeah. But I come to this in a minute. So what we did next is, we basically made one of these lines offset to and always in the opposite direction. So if this goes to the right, this goes to the left. If this goes to the left, this goes to the right. And what you can see is these two offsets cancel each other. That means they integrate with each other. And you would say, oh, this is maybe a very unspecific integration or something like in the minestrone where all these veggies float around and then you eat them or something like this. It's not the case. It's extremely super specific. If we move this to the stream they don't attend, then you're back to good performance. What we believe is what matters here is object identity again. It's just the same as with the grouping we had in space. It's now in space and time. And it's extremely precise. And that's
I assume that if you play this slow enough, like people always see it, right? What is the threshold when you start seeing this versus not seeing this? Like, what is the speed that you need for this?
Okay, I can tell you, this is usually an ISI. This is all 20 milliseconds display time. Yeah. And the ISI is usually 20 and 30. If you go to, say, 50 or something like this, then you see single elements. And to show you how precise this is, we have this experiment. In this case, the streams go in one direction. So this is the center element, and then they go in this direction. And what you can see, subjects are quite good. Then we put an element here. They cancel each other. And what we're doing next is we're just adding an element here in the first one. And that changes the grouping. What you now see is two streams that start from the first frame on. Subjects are tending here to the right. And what you can see is basically you get negative performance because subjects are tending here, because they just see this element and you're plotting it smaller, performance smaller than 50%. This one goes into this stream, and for this reason, they don't integrate. So if you move the line from here to here, then these two are in the same stream again, and they cancel each other. But we believe is once more, and I need to tell you something. This is just 200 arc seconds away. This is really tiny. But the brain does a super good job. It's not that the brain just has some limits or here and cannot process stuff. That's what the brain wants to do, and I think it's going to do a good job because this is your stream. And the assumption is that all the elements belong to each other. And for this reason, you should integrate the information. And I think that's what we're doing all the time. Can skip. All the time. It's not running. It's just slow. That should be a car that moves. And, you know, things are always in motion. Yeah, no, I'm shaking my head and things like this. You always need to integrate information. And if you just look at one point, for example, you want to know about the color of the car, then actually, you know, this is very bad estimate. You know, you get all the spectral lights and all these type of things. And particularly if it moves fast, you get bad estimates. But if you know that this is one car, then you basically just estimate all the information along the motion trajectory, and then you average and you get a much better estimate. That's a little bit the idea. And I think that's what we're doing all the time. We're trying to get good information by averaging information of the features that belong to one object. That's the idea. So the object identity prevails, and that's what we have many experiments here that shows us that even over an eye movement, if you make an eye movement, you're still integrating information. Okay, but important for our point right now is that this integration is unconscious and mandatory. And the unconscious part I've shown you, the first element you cannot see, it's not blue, that's just for you here. It's actually white on black. And what we have here, basically, we can now move this anti-Burnley or the second Burnley until further and further ahead in time until you don't get integration any longer. That's the idea. Sure, if this comes after 5 seconds, you're able to see the two separately. So what we can do is we can present the two and see when it basically breaks down, when you can report the two. And that happens around, this depends very much on the subject. 290 is the shortest we found, usually goes to 420, even longer maybe. The subjects integrates this mandatorily, and we ask them to say report both offsets, and they can usually not do it, they just see one offset. So what we do next is, we have even more lines. We have more lines in general. And we added another offset here. And what you can see is the difference here between the two is 160 milliseconds, and the whole thing is 330. But what's going on to happen in this case is you see two offsets, and one is the integrated offset of the two, and the other one is this one. So you can report 2, not 3 offsets, but this one is rather 50%, and this one is basically what you're going to perceive. And what we believe is there is this processing window, call it a window of sense making, where information comes in. As I said, you keep all the information in your little basket, you're not conscious about it. And then at the end, you say, oh, that's what I have perceived. And that's the integrated perception about everything that happened during this epoch. And then the next window comes. And for this reason, you can report this offset independently. And what matters is in which window these offsets are, and not the spatial temporal proximity, because these two are closer to each other than these two. That's the idea. And that's what I believe are the fundamental processing units of the brain. It's extended periods of unconscious processing, where information comes in to your brain. It's a little basket or a video if you want. You watch the whole thing, you compute things, and at the end you say, that's what it was. And the important thing is that this basically implies that conscious perception is not continuous. We are not continuous at each moment of time, but only at certain moments, at certain snapshots, but these snapshots integrate the information what happened before. This is not a surveillance camera that just makes a photo every second. It has everything. I think the unconscious, just one thing, the unconscious processing goes on forever. You're just extracting something, sometimes some type of information. It's like a captain on a ship that calls the people in the engine room and say, what's the temperature or something like this. Then the captain has an estimate and then it updates the estimate. That's a little bit the idea.
Is the idea that you, like, let's just say if you have 10.0 and 10.4 milliseconds, that at this point you basically see the feedback from over time frame, or do you literally see a snapshot at that point where?
No, you see what happens. It's a compressed information what happens. So my metaphor is always, if you return from vacation and someone says, oh, what happened? And they say, oh, we were 2 weeks in Tuscany and on the first day it rained, and on the third day something like this. So the information is totally compressed in some way. Basically, it's a compressed information. The person who asks you is the consciousness, your consciousness in some way. So you have all this information, but the person learns about your vacation, that's conscious information. And I think it cannot be otherwise, because he cannot see motion, particularly not apparent motion, before the second element has appeared. Yeah, if you have a disk here and a disk here, usually we see this one first, motion, and then the second one. But logically, it's impossible to see motion before the second element has appeared. And that's what we believe is, we believe the information is there. But if it is in your buffer, in your unconscious buffer, you can say, yeah, my best interpretation is something basically moved from left to right. That you cannot do in a continuous, if you believe in continuous consciousness. That's the idea. So things, we don't perceive things when they happen, particularly not motion. We just see things after they have appeared. And also, if there are two elements, you're not integrating them. We're not saying everything is integrated, we just say it's sense making. So if two events happen, like a red line for 20 milliseconds and a green line, you're not conscious of them when they appeared. You're just conscious of them later on, and you're reporting or you get a compressed representation of the entire event, like with the vacation metaphor. Okay, that's basically the idea. That's what I said. Okay, good. So much to this. Now we come to if you find this crazy, you don't know what's going on to come. So where are we? We said this bijection is not valid. We are not so acquainted. I'm not saying there's no external world, don't misunderstand me. I'm just saying the relationship between what's out there and what's in is not that simple. I think I showed you a couple of examples, and we're definitely not perceiving things just when they are presented. This is an illusion. I think we know, at least what I'm proposing is what the fundamentals of processing are. There's this idiosyncratic discrete processing. So that we know. The big question is, what is actually out there? And usually we believe what's out there is what we can perceive, but we just learned maybe perception is not the best guide to tell us about what's out there. So we cannot perceive what's out there. But the big question now is then, do we have a chance to know what's actually out there? And maybe the philosopher Kant is right. Maybe we should not even start talking about these type of things. But I think we know actually what's out there. Yeah, so Kant might have been correct in saying, forget about it. But I think we know what's out there. Because, you know, we are natural scientists, so we are physicalists in some way. You need to believe in physics. Otherwise, you cannot put a person in a scanner and say, I don't believe in physics. That doesn't make too much sense. At least, but turn this way. If you're a physicalist, you know what's out there. We know that that's what physics tells us. There's these fundamental particles, which are fermions and bosons. The fermions and the bosons, so there's like these quarks and the photons and things like that. I'm not an expert on this. It's not so important. So we know what's out there. We know what actually the state of the world is at this moment, at least in principle. There's a, maybe I should show this in the future. There's an equation that's that long and not that heavy mass. And that tells us at which state the world is right now. It tells us about the spin of all the quarks in the universe and about all the forces and so on and so forth. So in principle, we cannot solve the equation. But in principle, we know, or at least physics tells us, that is an equation that tells us what the world is. That's the point. So we know about it, if physics is true. But it seems to be that's not going to help us too much for our question about perception, because here we have our candle. Yeah, we know the candle is nothing else as photons and as fermions and bosons, or atoms, whatever you want. So, but still the whole thing is a bijection in one way. So we don't gain too much, but that's not true. The argument is that actually there's many world states that give rise to the very same percept of the candle. Yeah, I just need to swap a few molecules here and so on and so forth. Things you cannot distinguish. So this is then not a bijection any longer. That's a projection. It's a many to few mapping. And that changes the picture entirely. Because now we have many states and we have fewer representations. And that means you can basically come up with extremely many representative systems that are totally uncorrelated. And my example is here. So this is our toy example. So assume we have 4 world states, whatever this is, and we have a participant or a person that has only 2 representations. One is a candle, and the other one is a face. Once more world states than representations. So the mapping is totally undetermined. So for example, for this person, it might be that the first 2 states go project onto the candle, and the 3 and 4 go to the face. The person never knows what's going on in the world. You cannot invert it. If this were a one-to-one mapping, you can invert and you know what's out there. But in this case, you cannot. You don't know how many states there are. Maybe there are millions, or maybe just one. You don't know. But what's more important is we can have another participant or another person, and this is totally uncorrelated. So in this case, actually also the world state 1 goes on the face here, not on the candle, but the world state 2 goes on the candle in both, and the 3 and 4. You can guess what's going on to happen. So in half of the cases, these guys agree. In the other half of the cases, they do not agree, or they perceive something totally different. If you now believe that objects are mind independent, then you would double the ontology in an extremely unhealthy way. Because we know what you're going to perceive depends on the world state, but also on the mapping. This is all about the mapping is the brain wiring. These 2 people perceive the world differently. So if you believe that what we perceive is really what the output of perception is, then in one of these cases, you have a candle in the world and a face. And I can have millions of these perceptual systems. I would enrich your ontology to an extremely large amount. And so for this reason, what I believe is that perception is actually a projection from the high dimensional world of physics directly into the mental representations. So the objects are the outputs of processing and not the inputs. So there is no space for a world in between where we have particles and then objects. So we cross this out. Once more, otherwise we have not only doubling and multiplying of our ontologies. These things don't exist. What exists is only this, which we cannot see. And the objects are the output. That means the ordinary objects don't exist. So it's not an idealistic version like Kant or Hegel. And there is something out there, and it's mind independent. But the objects are the interpretation of this mind independent world. And they have no ontological status themselves.
You would consider this the conscious perception?
It doesn't need to be conscious. That would work for unconscious perception as well.
I agree with you, but I want to play devil's advocate here.
Sure. You can also disagree.
No.
Although almost everyone disagreed on this, so I'm used to it.
Yeah, I agree with it, but what objects, just for the sake of flying, we just said particles arranged in specific configurations are objects.
Yeah.
Just for the sake of language,
Yeah.
would that fit into your framework?
Yeah.
Cool. Yeah.
Sure.
Yeah.
Objects are compositions of particles.
Yeah.
But how you combine them is not only a matter of physics, it's a matter of perception too. I'm not saying everything is possible. Maybe there are combinations or there are world states that do not give rise to a unicorn. The unicorn does not exist in general. So I'm not saying everything is possible, but I'm saying there is no unique solution. It's like there's an equation, x plus y is 12. 36 and 15 are not going to do a good job here. But there's not a unique solution. 8 and 4 is doing a good job, and 6 and 6 is doing a good job too. That's what I'm saying. There are many interpretations of what's out there. And actually it depends on our brain wiring, and we all know that we don't perceive the world as it is because there are large individual differences. That's a little bit the idea. And if you look at different species, they become even much, much bigger. That's a little bit the idea. That's why we should refrain from thinking about objects. So the question is this...
Can I just quickly?
Yeah.
I mean, I think all of us here would agree that there are now two Michaels giving a talk here, right? So in general, the sort of low dimensional projection of this high dimensional space seems to be uniform across all of us.
Yeah.
But you seem to make a point that could be different because brains are wired differently.
Yeah.
But
then you would see...
I don't see the connection here. Or maybe I just didn't
No,
get it.
it could be if I just wiring the brains differently with magic power, then basically you would maybe, instead of perceive me, you would perceive Jenny. And you would perceive Jenny and me the other way around. I can swap these things. That's the idea. I can create these creatures by training a network. It doesn't need to be super deep. But I can create perceptual systems that are fundamentally uncorrelated.
Just basically like it doesn't, something converges because there's just irregularities in the models.
Yeah, sure. But what I'm saying is, yeah, you cannot see things that are not out there. But that I agree on. So there are constraints. I'm saying it's not white noise where everything is possible. But still, on the manifold of things that are possible, I can wire things in a way that is totally uncorrelated for all of them. If these systems will survive is a different issue. But at least in my little computer, I can keep these creatures away. I can also create little robots that totally disagree on things. That means the objects my little robots perceive are different in some way. And that's why they cannot be in the external world. The objects exist, they exist for you, and there is something that exists, which is the world. You're just interpreting it in a different way. Maybe if you want perceptions like a poem or something like this, or painting, different people see it differently. But the true thing you cannot see because that's physics, and we have no access to physics. That's the idea. So what you can believe, you can say right now, oh, maybe this is just philosophical, blah, blah, blah. Maybe it is, but I think a couple of things why I think that might be actually interesting for us. Let's look at this once more, and I'm done in a minute, sorry. Because I'm running a little bit out of time. So the idea is basically, in our scenario, there is something external world, or in our psychophysical experiment with this square, and then we clean it up, and then we're ending up with a square. That's the idea, what we think what we do in neuroscience. And then we're finding the neural correlates, we're sticking electrodes in it, and we try to find the correlates of this. But if this doesn't exist, then the situation is a little bit differently. And I think that's actually, I think maybe there's a fallacy here, what we may be looking for something that doesn't exist. And here is my slide for recordings from Carlos Ponce. And what they did is they have a monkey, and they're not going to present stimuli that they picked. Yeah, usually what we do is we pick the stimuli, like a square or a vernier, because we believe that's in the external world. But it's not in the external world. That's what I'm perceiving. I'm testing what the participants perceive relative to my perception. So they try to find an independent approach where they present stimuli that are not interpreted at all. And they start with some stuff and they present it to the monkeys. They record from a neuron and they find the images that basically drive the neurons best. And you would expect that particularly in higher areas, they're going to converge to whatever, phase neurons, candle neurons, and things like this. But that's not true. What they found is basically you started with these images and then they created new images in a closed loop manner. And then something like this happens. And that's what the outcome is. So this is different neurons. And takes a while. And then they come up with this type of stimuli. But that's not, at least not something what I would say is part of my objects. This is just something else. So these are the image that drives this neuron best and this and this. Okay, you can never know, maybe there is something, but none of these neurons shows something even close to an object. So when we record from neurons and say it is a phase neuron, yeah, it reacts also to phases, but maybe that's not what really the stimulus drives. So basically we just getting out what we just put in. We thought, oh, we're looking for phase neurons, and that, you know, some neurons always fire and you're going to find them, but that's maybe not what the neuron's coding for. So in some way, we should have not talked only about two fundamental questions of perception, but there's three. So actually, what's out there? Usually we think that's what perception tells us, but we saw it's not. There's a question what's actually going on in the brain. It's also not that we perceive things as they are. It seems to take a long while. But maybe even the brain codes things very, very differently than we believe. Maybe that's really not this super simple bisection saying, oh, you know, there's a candle in the world. We're finding the candle neuron, and that's why we perceive the candle. Maybe there's no candle neuron in the brain at all. Sure, there is a representation for a candle, no question about this. But it doesn't need to have candle-like properties or shapes or something like this. There could be a foyer or whatever. Maybe the brain is not coding these things in the manner we believe it's going to code for. That's a little bit the message here. Okay, I'm skipping the 2 slides because I'm really too long. I think more or less everything what I said. I think what's out there is what physics describes us. We cannot see what physics is doing. The objects are the outputs of perception. And I think the fundamental perceptual processes are time-consuming long processes, maybe up to 400 milliseconds. And yeah, that's more or less the main message. I'd like to thank the Swiss National Science Foundation, who's actually willing to support this type of research, which in these days is not a given, not applied research. It's crazy. So I think they're quite supportive of this, and I really like to thank them. And I'd like to thank you for your attention.
Thanks a lot, Michael. So I think we're slightly over time, so if anyone needs to head off, just please do. But I think, do you have time to stay for some questions?
Yeah, sure.
Yeah, so we could have some questions or discussion about some of these controversial ideas.
If I go.
Yes, good.
Nice to talk, first of all. Probably not understood everything you said, and hence my confusion, but you're arguing that objects are not central, they're kind of the outputs.
Yeah.
But then that one of those early crowding experiments you presented with the flanking squares, and you know, the more you have the flanking squares, that they seem to be grouped as objects and segmented out. So that implies quite an important role for objects in perception. And so I'm then confused by the statement that objects are not central to perception.
This is a good question. The question is this theory self-consistent? And of course, I'm arguing at the beginning, I'm arguing exactly as what I'm destroying at the end and saying, oh, there are no objects. But the theory, I think, is self-consistent. What I'm saying, for example, here is, this is what I believe is going on in your brain too, because we are clones in some way. Of course, if the individual differences are large, then you're making a mistake, and I think we're making often mistakes by this. But still, I can test you under the assumption that we have the same brain. I don't know what's out there, but under the assumption that you're reacting to things that out there in the same manner as I'm doing it, as an experimenter, then I can do this experiment. But I agree with you, as soon as our brains too different, the conclusion of these type of experiments are not warranted at all. And if we were doing this with octopus, I would say octopus is not going to do that. I think if you do animal research, I'm not sure to what extent this is really telling us something about perception in general. I think monkeys is fine. I think recordings from octopus brain potentially don't tell us too much. That's my feeling, because we are too far. So I can reconstruct everything what I said, that at least what I believe, in terms of a closed loop type of experiment that I'm testing you through my expectations. Otherwise, I agree with you, then there is a problem. And I think there is a problem, methodologically.
But my question was about objects, not individual differences. For me, that's a separate issue. Objects, unless you mean objects as physical objects.
No.
You can have objects in perception.
Yeah, but
and I'm not even talking about individual differences, but just about a separate issue. But this idea that perception revolves around objects, and that's quite fundamental to scene analysis. And
yeah, but my point is, I'm not saying this is there is something in the external world that corresponds to this. And this is my percept of this. So it's the output of this processing. So it's an object in my mind, if you want, or that's the interpretation I have about the world. And I assume you have the same interpretation too. Then I can do the experiments. And then I can also talk about objects, because I know there is something out there that corresponds to this. There are actually many states. And if you basically have the same projections, the same wirings, then you're projecting the same world states on this. So I can bypass the world in these type of experiments. That's the idea. But that only works if our wiring of the brain is rather identical. If not, then I agree with you. Even this type of argumentation is not true. And I think it's true to some extent. Think about the dress or something like this, where actually the perception differs quite a bit. And look at Jenny's color differences. We need to be careful about this, because the same object in the world does not lead, the same world state does not lead to the same percept.
So you're talking about these different world states, right?
Yeah.
I'm thinking about like what about psychedelic states or like schizophrenic states.
Yeah.
Basically, people that are under psychedelic influence, they swap between different world states, and that leads them to perceive things.
Okay, that's a good question, and we don't know. It could be that, for example, psychedelics really changed the world, how we perceive the world in a conscious fashion. So it really targets consciousness. But it might also only target the content of consciousness in some way. It might be that actually, this is what we just talked before, you just have a different brain then. And then it has nothing to do with the final percept in some way. It just has something to do with changing the early stages of vision. For example, I'm not an expert in this, but I think LSD changes the wiring in V1. Then this has nothing to, this is basically just a different brain for a while, the time when you have consumed the drug. So it's about the content in some way. So you're changing the brain to octopus in some way. That's to be a little bit radical in this. So we don't know this. I think it's a good question if it really goes onto consciousness directly or something like this, or it's just changing the content of consciousness.
I wanted to ask about the sort of 400 millisecond epochs over which you integrate conscious experience. Do you think those epochs are just an ongoing thing, or are they synchronized to stimulus onsets, for example?
Okay, this is the question that is bothering us for a super long time. So of course, in the natural world, and in the lab, it's easy. The window starts with the first element present in the screen, but that doesn't happen in the world. We try to find out what starts these windows. They're not successful. I thought it's related to eye movements. So with each saccade, you start the window new, but it's not true. I don't know. And we have done so many experiments on this, and it's a total failure. That we don't know. Second part of the question, it's not periodic. I'm not saying it's, and that we know, we have done experiments, and it's not the evidence, actually. You would expect a large vernier leads to a shorter window, but that's not the case. It seems to be that it's actually the processing load. So if you're in a situation with a lot of fog, like in the UK, then potentially the windows are longer than if you're in a sunlight situation. Then that we tested. So the brain seems to monitor how complex the task is and then adjust the windows.
Interesting.
Yeah. So what it is, we had a vernier and anti-vernier that cancel each other. So the performance is the same, but the workload is harder. And then the windows become longer. But these things are hard to measure. And that's something we work on right now. Also, if stress can actually shorten the windows and things like this that we don't know. Or if different personalities, we don't even know what test retest is. The only thing is that we know they are long, and they're much longer than usually what people believe. So not 30, 40 milliseconds, or maybe 100, it's definitely longer.
Okay, well, thanks again, Michael.
Yeah, thank you.
So just to mention again that this is part of a web-based talk series. So this recording will be on the Worldwide Neuro on the Sussex Vision page. So it will be on the web, on YouTube, definitely. So I'm I'm definitely gonna watch it again, because I think you've given us a lot to think about, so
Okay, I'm sorry.
thanks a lot.
It was a little bit too dense, sorry.
Thank you. Mitchie, I think we can probably end the meeting.
Yep.
No, Mitchie wants to do that. I think he's maybe in control of it from his other computer. Oh, thanks a lot for that, Michael. That was very interesting.
Thank you. I had love to talk about the individual differences, but that we can do next.
Yeah.
That's even more provocative, the talk.
Yeah,
This is more crazy, not provocative.